Hello, welcome everyone. In the last class, we learned about how to use energy methods to find out displacements in structures, displacements or rotations or angle of twist and so on. So in this class, we'll look at a specific example of how you can use these methods to find out the displacement of a structure. So what are the objectives? Essentially, in this lecture, we will learn how to use the equivalence between the work done by the external force or a moment and the internal strain energy to calculate displacements and rotations in structures. Okay, so let's look at the specific example we have in hand here. Okay, so in this case, we essentially have a L-shaped structure. It is a hollow structure that has an inner diameter of 40 millimeters and an outer diameter of 60 millimeters. Okay, and essentially you have a 600 Newton force acting vertically at point C. And you're given the Young's modulus of this material is 200 GPa and the shear modulus is 75 GPa. And you're asked to find out what is the vertical deflection at point C. Okay? The first thing that I want to point out here is that in this particular structure, you have only one force acting on the entire structure. So essentially, you can use the energy methods that we learned in the previous lecture. Okay? And the second thing is that it is asking us, the problem is asking us to find the displacement at point C in the vertical direction. So it is in the same direction as in which the force is being applied. So the force is applied at point C and we are asked to find the deflection at point C in the direction of force. So when all these conditions are satisfied, then we can essentially use energy methods. Okay. Now, if you want to use energy methods, the first thing we have to do is find out what is the internal strain energy that is present in the structure. Okay, so you're given some of the dimensions, like 800 millimeters is the length of segment AB and 400 millimeters is the length of segment BC. Okay. The first thing we have to notice here is that the segment AB is going to have both bending and torsion, whereas the segment BC is just going to have bending. So essentially we have to find the bending strain energy in BC and we have to find the bending as well as torsional strain energy in AB. Okay. So how do we go about doing that? So let's just first look at the segment BC. Okay, so what I have done here is that I have isolated this segment and this is point C where the force of 600 newtons is being applied and the coordinate system is given like that. Okay. So here, one thing that I have done is instead of using X as my coordinate, I am coming up with a new coordinate x prime which goes in the opposite direction of x. And the reason that we have this local coordinate x prime is because it actually makes the moment function a little bit simpler. Okay? So what we do is we look at this segment CB, we take a cut and then we look at the free body diagram of that cut. And that is how the free body diagram looks like. Right? You have a force of 600 newtons acting vertically. To counteract this force, essentially, you have to have a moment, My, acting this way. So to be precise, there has to be also a shear V, but in this class, we ignore the energy associated with the shear force. Okay? But if there is a force acting like that on the left-hand side of the body, then the internal moment has to be in this direction. Okay? And that My is going to be nothing but 600, which is the force, times the distance x prime. Okay. Now, the 600 x prime moment is actually a negative moment because if you look at the right hand rule, if you rotate your, if you curl your fingers in the direction of My, your thumb is going to be pointing in the minus y direction. That is why My is minus 600 x prime. Okay. But anyway, so the main thing is that we have found the bending moment in the segment CB as a function of x prime. Okay. Now let's go and look at the segment AB. Okay. So what I have done here is draw the free body diagram for the segment AB. Okay. And here again, I have used the local coordinate y prime, which goes in the opposite direction to y. And the reason that we use this local coordinate is because it makes the moment function a little bit simpler. Okay. So if you draw the free body diagram as I have drawn here, and then you use the sum of moments equal to 0 and the sum of forces equal to 0 along all three directions, you will find that the moment along the x direction, the internal moment here, that is what I'm talking about, that mx is given by 600 times y prime. Similarly, the moment along the y prime direction, which is actually a torque. So this is a torque. So that ty prime, if you calculate what it is going to be constant irrespective of the coordinate y prime. So at any section here or here or here, irrespective of what y prime is, the torque applied by the 600 Newton force is going to be a constant. And that is going to be 240 Newton meters because it's 600 times 0.4 meters, which is the length of the arm. So essentially, what we have done here is we have found out what is the bending moment in segment BC, as well as the bending moment and the torque in segment AB. Okay. The one thing that I want you to notice here is that the bending moment in BC is my, whereas the bending moment in segment AB is mx. So essentially, because the segments AB and BC are in different directions, the directions of the moment, what is the bending moment and what is the torque in each of the segments, is going to be different. So that is something that you have to keep in mind. Okay, now we have found out the torques and bending moments, and these are the internal bending moments and the internal torques, and that is what we require to find out what the strain energy is. Okay, so to calculate the strain energy, first we have to calculate some geometrical parameters, which is your polar moment of inertia J and the area moment of inertia I, because this is required to calculate the torsional strain energy and the bending strain energy. So what is the torsional strain energy? The torsional strain energy is nothing but the integral over the length of t squared over 2gj times whatever variable you are integrating over. So in this case, we are integrating over the y prime axis. So that is why this variable is dy prime. Okay, so you do that. So in this case, the torque is constant, just 240 Newton meters. So it's 240 square times dy prime divided by 2 times gj. G is given to be 75 GPa and j we just calculated. And the distance that you have to integrate is from this point on till point A. So the distance AB is 0.8 meters, and that is why the integral goes from 0 to 0.8. Okay, so essentially we are integrating this over the segment AB. So let me also write it down, and this integral is over segment AB because the torque is present, the internal torque is present only in the segment AB. Okay. Now let's do the same thing for the strain energy for bending. The general expression for strain energy due to bending is m squared dx by 2ei from 0 to L. In this case though, you are going to have a bending energy, strain energy both in AB and BC. So this term here corresponds to the segment AB, and that term there corresponds to segment BC. Okay, and these expressions were the ones that we derived just a few minutes back. Okay, so essentially what we do is we take out the expressions for the bending moments in AB and BC, put it into the integral, and then perform the integration. Okay, and if you do that, the strain energy turns out to be 0.3385 joules. And the strain energy in the case of the torsional strain energy turns out to be 0.3009 joules. So essentially, we have calculated the strain energy both due to bending as well as torsion. Now essentially, we have to add them up to find out the total strain energy. So essentially, Ui, which is the total strain energy, is Ui due to torsion here, plus Ui due to bending. Okay, and that sum turns out to be 0.6394 joules. Okay, and one thing that I want you to pay attention is that when you calculate the strain energy, make sure that you get your units correct. So for example, if your moment is in Newton meters and your distance is in meters, then essentially you get the strain energy in joules. On the other hand, if your moment is in Newton millimeters, for example, then you have to multiply by a factor of 10 to the minus 3. Okay, so just make sure that the units are correct. Okay, so now we have found out what the total strain energy is. In this case, the strain energy has to equal the work done by the force P. So if you look at, in this case, you essentially have only one force of 600 Newton acting on the structure. So half P times delta, which is the work done by the force, has to be equal to the strain energy that we just calculated. So in this case, P is 600. Delta is unknown. That is what we are interested in finding out. So half times 600 times delta C should be equal to 0.6394 joules. Okay, so if you use that equation, essentially you get delta C to be 2.13 millimeters. Okay, so in this case, what we have done is essentially we can take the strain energy in the structure, we calculated that, we found out what is the work done by the force, we equate them, and that essentially gives us the deflection due to the force that is caused on the structure. Okay, so we will look at more examples using what is called as a Castigliano's method in the following lectures. Thank you.